Year 12, here we are in the last of the videos for this topic of exponential functions. Rightio, and it is applications of integration. We integrated some functions last time, and frankly, I think they're pretty good in terms of integration. I think exponential functions are relatively easy to work with. But what I think, well, that doesn't really matter. We are going to look at there are a few different things we can do here. So many of them are so similar to what we have done previously with integration just recently that I'm just going to look at one of them here. Right, save down on time. We'll work through some others in class, particularly if you've got some questions about them. But for the time being, I just want to look at this one example, and that's going to wrap it up. Okay, so what I want to look at is I have this function here. It's like the exponential with a little bit of a shift. We need to sort of sketch that. We need to work out what's going on. And we're going to do that because we want to work out an area. Okay, we want to work out an area, and that doesn't really work unless we've got a bit of a sketch. It's always sensible to do that. So, we have y equals e to the x minus e, and I much prefer to write these things as y plus e equals e to the x. Right, and I compare that to my sort of basic function, and I say, right, what's happened here is I have shifted down e units in the vertical axis. Okay, so this is y equals e to the x shifted down e units. Right, so what does that look like? Right, let's use some space and sketch it. Right, it's going to go, so I'm going to have an asymptote. It says to find the asymptotes. I'm going to have an asymptote here at y equals negative e. Okay, negative e there. And that means that it's going to sort of go up like this. Right, normally it would go here. It has been shuffled down about 2.7 units. Now we should do a couple of things. Let's find some intercepts. Right, that's driving me crazy. I need to put these things in. Let x equal 0. That's always a good one. Let x equal 0. Where does it cross the y-axis? If x equals 0, y equals e to the 0 minus e, which is 1 minus e. Okay, so I'm going to cross 1 minus e, right, so that's about negative 1.7. It's going to be down here somewhere, right, somewhere between the origin and this point here, which is negative e. It's 1 unit above here. Okay, so that is 1 minus e is where it's going to cross there. I've still got this asymptote here, right, I've got an asymptote, I've got one of my intercepts. It is going to come up here, it's going to cross this, right, it's going to cross the x-axis. Right, because we have fallen down below it now, it's no longer the asymptote, it's going to cross it. Now, let y equal 0. Therefore, e to the x minus e equals 0, right, which is the same as saying e to the x equals e. Now, strictly we would solve this with some logarithms, but, right, I think we can just equate these things well enough and say, e to the x is the same as e to the 1. Can we say x equals 1? Sure can. Right, x equals 1. So we have an intercept here at 1. I've got my asymptote, I've got my intercept, and I know that's the general curve here. So it's going to go whizzing down here, and then along there. There's my asymptote. Okay, so that's 1 there. That's 1 minus e there. There's my asymptote. So it says showing the intercepts and the asymptote. Well, I think I've labelled that well enough there. There's my intercepts, 1 minus e and 1. And some working to support that. I reckon that's pretty good for part 1. Part B, find the area of the region between this curve, the x-axis and the y-axis. That's this part here, isn't it? Okay. So, this is below the x-axis. So typically we would get a negative answer unless we were to run this back to front. So I'm going to say, what we're going to find is the integral, not from 0 to 1, but I'm going to say from 1 to 0. If I run that backwards, it's going to give me the positive. You could go from 0 to 1, put the absolute value there, that's fine. Of e to the x minus e dx. Okay, so I need to integrate that, and I get, well, e to the x, wonderful. And if I differentiate this, remember that's a constant. Okay, so that's like, imagine that was 2, it would be 2x. So it's minus ex. Right, I don't need a constant of integration because this is a definite integral. I substitute these things in. A little tip, something to keep an eye out for. I have noticed a number of people making mistakes sometimes where when you substitute the value for 0 in, that it's non-zero, right? Sometimes when you do that second part where you've got to do the subtraction, people just assume it's going to be 0 and they forget to make that subtraction. With exponential functions, that's far less likely to be the case. It's quite unlikely when you substitute 0 into an exponential function that you get a value of 0, whether it is the integral or the differential or anything else, right? Very unlikely that function of 0 or the f dash 0 or anything else is equal to 0. But anyway, just something to keep an eye out for, because I have seen that mistake creep in a few times. So we're going to want to substitute 0 in first. So I get e to the 0, which is 1 minus 0. There's my first part. And from that I subtract e to the 1, which is, e to the 1 is e, and minus e times 1, that's minus e. You know, see, it's 0. I get an answer of 1 square unit. How neat and tidy. Wonderful. Anyhow, that's how you can apply some of these integration techniques to exponential functions. Of course, we can do revolutions of solids and areas between curves and whatever else. Fundamentally, that's the same as what we've done in integration before. We will have a look at those in class, and I'll put some on the board and you can work through and ask some questions, but I think that'll do for our video. I've been talking quite long enough. So now.